Hello, everyone, and welcome to another AP Chemistry virtual lesson. My name is Michael Faribaugh, and I teach AP Chemistry at Albemarle High School in Charlottesville, Virginia. If you missed yesterday's lesson, again, this is AP Prep Week, I had presented some sample questions, and then I presented a timed experience for students to take. So if you missed yesterday's lesson, you can go to tinyurl.com/AP Chemistry sample questions, and the link is listed in the video description. I would strongly encourage you to stop this video and to actually take the time to answer those questions, sample question 1 and sample question 2, which you can find in the folder at this link. Because I'm about to go over the answers to the questions. So if you haven't solved these questions yet, it's not going to be very helpful just to watch me solve. But if you were present and you did solve these questions, I'm going to go over the answers. Now, one of the things I'm going to say before I start to go over the answers is, let's talk about the format of how you might submit your responses. Remember that you can either copy and paste your response from a document into the window and then submit. You can attach a text document, or you can attach a picture of your handwritten work. So here are some examples of what I received in my email yesterday from student responses. So the concern I have with this is a student is trying perhaps to put everything in one spot, and I don't think they're giving themselves enough room to show their best work. So I would strongly encourage you to, if you're going to handwrite, to write on white paper, whether it's lined or unlined, but try to use a decent font size. Here's another example where there might be some really good chemistry here, but you're going to make it difficult on the reader who is trying to give you credit. So I would try to encourage you at this point to write your answer a little bit larger font size. This was also some work I got, which again, if you try to blow this up and expand it, it might make it a little bit easier, but I would encourage you to use a dark blue or black pen or a dark pencil on white paper to make it easier for the reader to read. This is a little better. This is, again, evidence of handwritten work that's a little easier to see because of the contrast. Now, some students did not handwrite their answer, some typed, but do not be concerned that your typing has to have all of these fancy formulas and subscripts. Okay, you can still show your work without using fancy graphics. This person typed, but I have a problem here in that they have numerical answers, but they have not shown any work. So on the AP Chemistry exam, if you need to do a calculation, you have to show us some kind of a work about where you got your answer from. Again, same thing here. There's some good descriptions, but again, if you just give an answer without showing how you arrived at that answer, you're not going to get full credit. Now, this is fine. Here we have a student using the ideal gas law, N equals PV over RT. That is sufficient. We don't need to see subscripts on CO2. We know what that means. Here we have a conversion factor that goes from grams to moles and from grams to milliliters. This is fine. So you don't have to do anything more. This is totally acceptable for showing your work. Again, here we know it's supposed to be MC delta T, looks like a capital A, but that's still recognizable. So this is a fine way to show your work. Okay, you can do it all on one line, so you don't have to do fancy subscripts or formulas. So I strongly encourage you, if you're going to type, to show your work. Don't just give us a numerical answer. All right, let's go ahead and take a look at sample question number 1, part A. Ethanol will combust in air according to the equation below, and the question asks, is O2 gas oxidized or is it reduced? The correct answer to this question is that oxygen is reduced because the oxidation number of the O, the oxygen, changes from 0 in molecular oxygen to -2 in carbon dioxide and water. So I'll show you some sample student responses for part A. This looks good to me. Oxygen is reduced from 0 to -2. Another student saying oxygen is reduced. It has an oxidation number of 0. And then in both CO2 and H2O, the oxygen has oxidation number -2. Okay, here we have some concerns about, excuse me, student responses. They did say that oxygen is reduced, but they said from 0 to -4, and that's incorrect. Here we have a change from -2 to -4. So again, they have to justify the answer in terms of oxidation numbers. This says it's changing from 0 to -1. And then we had some students that thought that oxygen is oxidized as it goes from 0 to -4, or that it's oxidized as it goes from 0 to +2, or that it's losing electrons. And then we have students that even though the question said, is it oxidized or reduced? It's almost like they didn't trust the question, or they thought it was a trick question. They said it's neither oxidized or reduced because it's -2 on both sides of the equation. It remains at oxidation number -2, so it's neither oxidized or reduced. So don't try to outsmart the question. The correct answer was that oxygen was reduced from 0 to -2. All right, part B. When a sample of ethanol was combusted, the volume is 18 liters. The temperature is 21.7 degrees Celsius, and the pressure is 1.03 atmospheres. So in my opinion, when you have a volume, a temperature, and a pressure, this sounds like a good opportunity to use the ideal gas law. And on your equation sheet, they're going to give you the value of the ideal gas constant R. So many students did this successfully. You do have to consider the fact that the temperature was not given to us in Kelvin, but rather in Celsius. All right, so I'm going to go ahead and rearrange the ideal gas law. N equals PV over RT. Plug in the information that was given to us in the problem along with the ideal gas constant and the conversion from Celsius to Kelvin. So I'm looking for an answer for moles of carbon dioxide that is approximately 0.767. Let me show you some student responses. All right, this person set up their work. I can see everything, including the temperature change from Celsius to Kelvin, 0.767. Again, same thing here, 0.767 moles. This one typed their answer. I have no problem with this. Everything is done on one line, but it all looks like it's correct in terms of the setup. So again, don't feel like you have to handwrite your response. This looks good. This person has a good setup, except for the fact that they have left their temperature in Celsius, so they got the wrong answer. Interesting thing on this one, I see everything correct in terms of numbers. And yet, instead of getting 0.767, they got 1.31. I think they just somehow inverted the numbers. So instead of solving for 1.03 times 18 divided by R divided by T, I think they flipped that upside down and got 1.31 instead. So again, watch out for some simple mathematical errors here. All right, Roman numeral 2 of part B. So we have that 0.767. Determine the volume of ethanol in milliliters that was combusted. So we have to somehow convert from moles of CO2 into moles of ethanol. We have a balanced chemical equation for that. Then we can use the periodic table to go from moles of ethanol to grams. Then we can go from grams to milliliters using density. So this is our conversion from moles of one chemical to moles of another using the coefficients. Now we're going to use the periodic table. So we should have approximately 46 grams per mole if we add up the atomic masses of 2 carbons, 6 hydrogens, and 1 oxygen, about 46. And then we have 0.79 grams on the bottom and 1 milliliter on the top to convert grams into milliliters. And so we get around 22 milliliters. Nice setup here, 22 milliliters. Again, this is typed. All the unit conversions look good to me. 22 milliliters. So again, I'm just showing you that you could have typed or written out your response by hand. Just kind of showing you a variety of acceptable student responses. Here's a concern. They did ask for the problem to be the volume in milliliters. This person did great work. They have the right number, 22.3, 22.4, but they put L for liters at the end of their response. So that would probably lose the point because they have the wrong unit. So again, be careful for some minor mistakes like that that could cost you an easy point. I think what these people did wrong is they had somehow made a mistake in their calculation of the molar mass of ethanol. So they definitely have the mole to mole conversion, but somehow they got a number other than about 46 grams per mole for the molar mass. All right, on to the next part of part B, the Roman numeral 3, determine the amount of heat that is released. So we've got to convert moles of carbon dioxide into kilojoules of heat. Now you could just put 1270 on the top and 2 moles of carbon dioxide on the bottom. I'm doing this through the mole of reaction, but you could have just skipped this or combined this into one step. That's fine. I've got 0.767 divided by 2 times 1270, so I get around 487 kilojoules of heat released. I don't need a minus sign here, just the amount of heat that was released. All right, so here this person did it with typing their answer, looks good. I'm ignoring the minus sign, that's fine. 487 kilojoules of heat released. Again, you can see typed answers as well as handwritten answers. So these all look good. Again, just kilojoules over moles of CO2. All right, let's take a look at some mistakes. This is close, but they forgot to divide by 2, so they are off by a factor of 2, did not realize that there's 2 moles of CO2 for every 1270 kilojoules. And then this student is doing something converting moles of kilojoules into moles of water. And then somehow 1.15 changes to 1.9 when I'm not really sure what's going on there. So they have an incorrect answer for kilojoules. All right, part C of this question. 487 kilojoules is what we got for the amount of heat released. That is also equal to 487,000 joules. So pay attention to units now because we're going to determine the final temperature of the air in the room after the combustion. So we are given mass of air. We are given the initial temperature and we're trying to find the final temperature, and we are given the specific heat. So we're going to use Q equals mc delta T. So I have 487,000 joules. I am given the mass of the air in the problem. I'm given the specific heat of the air. So we're going to solve for delta T. Now, when I solve for delta T, again, watch out for units. I have joules. So the joules will cancel out. I will also have the grams cancel out, and I will have my answer in degrees Celsius. Of course, this is not my final answer, but rather the answer for delta T, 21.7 plus the delta T, which is about 8.7, gives me a final temperature of approximately 30 degrees, about 30.4 degrees. Let's take a look at some student answers here. This looks good, but I was a little concerned about this. They got the right answer, but notice they have kilojoules on the left and they have joules on the right. So somehow they were able to convert 486 into 486,000 and do that math. So they got the right answer, but that was a little concerning to me that somehow the units did not look like they were going to cancel out. All right, this person gets 30.4. I can see their work. Again, this is handwritten, but you certainly could have typed it in. Another example of the correct answer here. This person typed it. Again, Q equals MC asterisk delta T. That's fine. No fancy formulas needed. Okay, this all looks good to me. So do not be intimidated by trying to type in your response. Final temperature equals initial temperature plus the delta T, 30.4. Looks great. This person also looks good. They've got a typed answer. I see the 0.767 for moles. That was done all on one line. Looks great. I see that 22.4 milliliters. I see 487 kilojoules. They might have lost a point here because it's actually around 30.4. So 8.7, 2, and 21.7. You add them together, you get 30.4. So slight math error on that one. So be careful for little mistakes like that. And again, in terms of units, this person doesn't have kilojoules on the left. They don't have joules on the right. So they go ahead and just divide. And now they have a delta T, which is off by 1,000. So instead of a delta T of 8.7, they think the delta T is 0.0087. So they have actually assumed that the final temperature is actually about 21.7. Okay, and this person they wrote the problem and they inverted the numbers. They had 21.7, then they wrote 27.1. So again, pay attention to minor errors like transcription errors and little mathematical mistakes. This was exothermic, so it releases heat. That number looks good to me. I'm not worried about the minus sign, but they kept the minus sign around. And so instead of the temperature of the air getting warmer, that minus sign actually causes them to think that the temperature of the room is getting colder. Now, we know it's an exothermic reaction. It's a combustion reaction. So this person went the wrong direction with their delta T. So again, try to use some knowledge of what's going on. The room should be getting warmer, not colder, if the air is part of the surroundings. All right, the next part of the question is chemist wants to run the reaction and maximize the amount of the product. Identify 2 ways the chemist could change the reaction other than adding or removing chemical species. So keep that in mind. We're not allowed to add more C2H4 or more water vapor. That's already given to us in the stem of the question. How can we shift or favor the formation of the product? Justify your answer. So the 2 things we're looking for here are, you could decrease the volume of the reaction vessel because we have 2 moles of gas on the left and 1 mole of gas on the right. So because there are fewer moles of gaseous product than moles of gaseous reactants, decreasing the container volume would cause the equilibrium position to shift toward the right, toward the product. We are also given that this reaction is exothermic, so we could change the temperature, specifically by decreasing the temperature. That would shift the equilibrium in the exothermic direction. Okay, let's take a look at some good answers to this question. We have one that was typed. One way the chemist could change the reaction conditions to favor the formation of more product is to decrease the temperature. Looks good. Since the reaction is exothermic, when the temperature is decreased, system would favor the direction that produces heat according to Le Chatelier's principle, that is the forward reaction. A second way is to decrease the volume of the reaction vessel. Talks about fewer moles of gas. Again, this person says lowering the temperature because it will cause the reaction to proceed toward, they didn't say the word products, but we knew what they were talking about here, toward the right. Another way is to decrease the volume because it would shift toward the right. Now, take a look at this answer. They did not justify their answer. So the chemist can decrease the volume, but they didn't say why. The chemist can decrease the temperature. So those changes are correct, but they did not back it up with a justification. All right, increase the temperature to increase the number of collisions or to somehow increase the temperature so the molecules have sufficient energy. I think they're thinking about kinetics and not equilibrium. They're talking about somehow getting the molecules to collide or somehow giving them enough activation energy. So that's incorrect. And then watch out for this. This sounds good. Lowering the temperature. I like that. But then take a look at these phrases. Decrease the volume of the container is what we're looking for. Now they said increase the pressure, but there's lots of different ways you can increase the pressure. You could raise the temperature. You could add more of a particular gas, or you could decrease the volume. So increase the pressure is not specific enough for this particular shift toward the product. Okay, so be careful. Increase the pressure is a very generic term. It's not specific enough. All right, this person says, again, increase the pressure, but doesn't say why. This person says increase the pressure with an inert gas. Okay, so really you have to talk about decrease the container volume. Okay, so be careful. There's lots of different ways to increase the pressure. This person says increase the amount of water or increase the amount of C2H4. We were already given instructions in the question that we're not allowed to add or remove chemicals. Again, so pay attention to the stem of the question, read carefully so that you are answering the question that is being asked. All right, we now have another part of the question. We're going to go on to part E. It talks about a particular reaction, and this has to do with kinetics. So we have a reaction involving ethanol. We are given initial concentration of something called Cr2O7 2-, that's the dichromate ion. We're given the initial concentration of the ethanol, and they talk about a cuvette and absorbance, and we have this data. Our job is to calculate the value of the concentration of the dichromate ion at 1.5 minutes. So on your equation sheet, we have absorbance equals the molar absorptivity constant times the path length times the concentration. So what does that equation tell us? Well, what it tells us is that absorbance is directly proportional to concentration. So we could set up a proportion. We know that the absorbance was 0.780 when the concentration of dichromate was 1 × 10⁻³ moles per liter. And now we have a new absorbance value at 1.5 minutes. So we can plug in what we know, solve for the new concentration, which should be less than 1 × 10⁻³ because the absorbance has gone down. And we do this math, and we get an absorbance of 7.1 × 10⁻⁴. That's just a proportion. This particular value here, this constant, we did not actually solve for that, didn't need to do that, but you could have done that. So we could have solved for the molar absorptivity constant, and it works out to be about 780 based on the information from time 0. Then we could have plugged that in to the same equation, and we could have solved for the concentration at 1.5 minutes, and we still get the same answer. So we're looking for 7.1 × 10⁻⁴. All right, here's some student that decided to type in their response. Looks good to me. Again, I'm not worried about fancy symbols and superscripts. That's very readable and can be interpreted as the correct answer. So feel free to type your response. Don't have to worry about superscripts and subscripts. That all makes sense to the reader. This person has a proportion, and they got the correct answer as well. I'm happy with this answer, even though it's not properly formatted in scientific notation. I understand that 0.708 × 10⁻³ is the same as 7.08 × 10⁻⁴, so no concern on that. That's fine. This person made a mistake with their absorbance, so they got 0.708, so they're off by about, I guess, about 4 powers of 10 there. I'm not sure what they did wrong. I guess they just, yeah, maybe they're off by 3 powers of 10 there. So they messed up there. And this person has all the right numbers, but I think they inverted their ratio or somehow did not get the right answer because the absorbance is going down. We should have a smaller concentration than the original. Now this 1.4 × 10⁻³ is actually larger. So I think they might have just flipped this ratio. Again, watch out for some careless mathematical errors. All right, on to part F. A student claims that the experimental data indicates that the reaction is first order with respect to this dichromate ion. Do you agree with this claim? Justify your answer. Now, there are 2 ways to approach this. One has to do with the half-life. So 0.78 is our absorbance, which is representative of our concentration at time 0. After 3 minutes, the absorbance is reduced by half. After another 3 minutes, the absorbance is reduced by half again. So you could say, yes, I agree with the claim because the absorbance, which is proportional to the concentration of the dichromate, is halved after 3 minutes and again after another 3 minutes. Thus, the half-life of the reaction is constant, so the reaction must be first order with respect to the dichromate ion. Some students also decided to go down this road and they still got full credit. They took the natural log because that is part of the half-life equation, the integrated rate law. Now this takes a little more time, so I don't recommend necessarily this method if you're trying to go for speed. Constant half-life is easier to figure out, but if you can do this calculation and show that the natural log is decreasing by a particular value consistently over time, first order. So here is from topic 5.3. If a reaction is first order with respect to a reactant being monitored, a plot of the natural log of the reactant concentration will be linear. But you have to show your work. So just making a statement like that without showing the math is not sufficient. All you're doing is just memorizing a fact, but you're not showing us the actual data from the experiment. If the half-life is constant, then it's first order. So again, you have to say something about the half-life being constant. Now, some students said it has a half-life and therefore it's first order. Half-life is not unique to first order decay. Okay, the fact that the half-life is constant is part of that, not just that it has a half-life. Okay, so this person did make a graph to show that the natural log is decreasing over time. That looks good. This person says, yes, I agree, the half-life is constant. Yes, I agree, it has a constant half-life. I agree with the student's claim. It takes 3 minutes for the absorbance to half, and this remains constant throughout the reaction. Since absorbance and concentration are proportional, the half-life remains constant. Looks good. I'm not sure this answer gets credit. This might be a discussion at the reading. This is a little bit tentative, in my opinion. The person says, I agree that the reaction is first order because it has a half-life of 3 minutes. I don't know if they've established that the half-life is remaining constant over time. It just says it has a half-life of 3 minutes. It also says a graph of natural log gives a negatively sloped linear line, but they didn't show their work. Okay, so be careful on this. This person says, I agree, but I'm not really sure what these two rate constants are supposed to indicate. The person says, I agree. When the natural log from the experiment is calculated, the graph of natural log versus t results in a linear relationship, but that's all they said. They never actually showed that they did this math. Okay, so be careful. Just by saying that natural log of absorbance versus time is a straight line without showing how you did it is not sufficient. Okay, this person says the absorbance decreases by the same factor for each time interval. No, it actually, the absorbance versus time is actually a curve. It doesn't decrease by the same interval. Interesting comments here. I disagree with the student's claim because a first order reaction has a constant half-life, and according to the data, the table does not follow the path of constant half-life, so they are contradicting the data in the table. This person says, I disagree, although the absorbance shows a constant half-life. So again, I'm not really sure what's going on there. They understand the constant half-life, but they are disagreeing because they say the absorbance does not reflect the value of concentration. So again, some misunderstandings there. This is close. Again, I'm not really sure if they get full credit on this one. I want to think about this a little bit more. They say it shows a linear relationship, but we don't actually know where the straight line comes from. They didn't actually tell us what the difference is. So again, this is close. It says it shows a linear relationship, but I don't see a straight line. And I don't see the difference between these values. So again, be careful. These people are disagreeing because they say there's a coefficient of 2. in the balanced equation. Therefore, it cannot be first order. So they're confusing stoichiometry with rate laws. All right, next question, part G. Identify the intermolecular force that is most responsible for ethanol having a higher boiling point. We're talking about hydrogen bonding here in ethanol, which is not present in dimethyl ether. Okay, so looking for hydrogen bonding, ethanol can form hydrogen bonds between its molecules, whereas dimethyl ether cannot. The attractions between molecules of ethanol are stronger than they are in dimethyl ether. Okay, this looks good. I see hydrogen bonding, stronger IMFs. Okay, hydrogen bonding, stronger IMFs, looks good. This is close, but I don't think this gets the point here. Dipole forces did not actually say hydrogen bonding. Okay, so again, be careful that you identify all of the intermolecular forces. Some students thought that the molecule dimethyl ether was actually non-polar because of the way it was written in terms of symmetry. It's actually polar, kind of like water. It is bent. So it does have a dipole moment. All right, this one makes me a little nervous. It says the strong hydrogen bond between hydrogen and oxygen. This sounds like they're talking about a covalent bond. They do go on to say intermolecular attractions, but again, this phrase between hydrogen and oxygen, I can't tell if they mean within the molecule or between molecules. So again, be careful with your language. All right, on to sample question number 2. We are given 2 Lewis electron dot structures for SO3. If you look on your periodic table, you'll notice that sulfur has 6 valence electrons, and oxygen also has 6 valence electrons. We have 1 sulfur and 3 oxygens, so 6 plus 3 times 6, 6 plus 18 is 24. Looking for 24 valence electrons. If you count the number of valence electrons that were used to make the diagram that was drawn by student 1, you should see 26 electrons. So that's what makes student number 1's diagram incorrect. They have too many electrons. It should be 24 instead of 26. So student number 1 used the wrong number of valence electrons. Some students were confused on this question. They thought the student on the left expanded the octet of sulfur. This is not an expanded octet. This is just a normal octet, just the wrong number of electrons total for that molecule. Student 1 did not add the double bond. Student 1 did not account for formal charge. Instead of doing a single bond, they needed to do one double between one set of S and O. Again, talk about the valence electrons. That was kind of a straightforward question, but I think a lot of students didn't count the valence electrons. Not sure what's going on here. Oxygen has 6 valence electrons. The student drew all 6 electrons without allowing oxygen to form bonding pairs. Okay, student didn't minimize formal charge. Student 1 did not form a double bond. So again, it was just about 26 versus 24. Identify the hybridization of the sulfur in the Lewis structure drawn by student 2. So we have a total of 3 electron domains. If there were 4 electron domains, it would be sp3 hybridization. So because we have 3 electron domains, again, this is kind of like the molecule here. We have sulfur with 3 oxygens. And even though 1 is a double bond, we don't count that as an extra electron domain. So we have 1, 2, 3 electron domains, that's sp2. If there were only 2 electron domains, it would be sp. So a lot of students said sp2. If they got it wrong, most likely the wrong answer was sp3. And the student says the hybridization of the valence orbitals of the sulfur atom is the double bond. So they're confused between bonding and sp, sp2, sp3. The SO3 molecule contains polar SO bonds. However, SO3 is a non-polar molecule with a dipole moment of 0. Explain this property of SO3 in terms of VS-EPR theory and bond polarity. So here you should talk about the geometry. And here you should talk about the arrangement of the dipoles. Okay, so if the question is asking you to explain or justify your answer in terms of something, then that should be something you focus on in your answer. Okay, we're talking about trigonal planar and the fact that the bond dipoles in the molecule are arranged in such a way that they offset each other or cancel each other out. Okay. The SO3 molecule has a trigonal planar geometry. Sounds good. Allowing for 3 SO bonds to cancel out each other's polarity. I like that. The SO3 molecules, 3 bonded atoms, spread out the furthest they can be from each other, and because of VS-EPR theory, cause the molecule to be trigonal planar. Looks good. And completely symmetrical. Therefore, because the SO3 molecule is symmetrical, all the polar bonds cancel out, resulting in a non-polar molecule. Looks good. This is due to the molecular geometry of the SO3 trigonal planar, leaving the same charge in each end of the molecule, 120 degrees. The bonds are slightly polar, however, they cancel out. All right. SO3 is trigonal planar and balanced by the 3 oxygen atoms around the sulfur. Okay, so they never mentioned the dipole. I think it's nonpolar because it's trigonal planar is not sufficient, because I could easily draw a molecule that is trigonal planar and yet would be polar. So it's not enough to say it's trigonal planar. You should talk about the bond dipoles canceling each other out. SO3 is nonpolar because of the electron repulsion the oxygens have to each other. They spread out evenly, dispersing the polarity. They never actually said trigonal planar. Again, the oxygens even themselves out. So again, be careful with your language here. There's also resonance going on, but that's not the reason for the molecule being nonpolar. The fact that I can draw 3 equivalent resonance forms has to do with the bond lengths being equal, but it's not about the geometry. Okay, so don't confuse resonance and geometry. So the students on this slide are saying things like, although the SO bonds are polar, they exert equal amounts of polarity. I'm not really sure what that means, equal amounts of polarity. Again, talk about the geometry. Since all of the dipole moments cancel out, this makes SO3 a nonpolar molecule, but again, they never indicated the shape of the molecule. The geometry is trigonal planar, which makes a nonpolar molecule. Again, that's not enough. Then they go on to say that the bonds are distributed unevenly, or the electrons are distributed unevenly, giving oxygen a negative charge, giving the bond a polarity. So again, talk about the geometry. Okay, talking about, this is mentioning about LDFs. And again, it says to create an uneven, negatively charged cloud. So, okay, this is about resonance. It's not about the bond lengths being equal, it's about the dipoles canceling out. All right. This has to do with an equilibrium between SO3, SO2, and O2. A chemist fills a rigid vessel with SO3, and then the SO3 decomposes. So in the graph on the next page, we see the SO3 decreasing over time, and then the products, SO2 and O2, increasing over time. And at some point, somewhere in this range, the concentrations, or the pressures in this case, seem to remain constant over time. Estimate the time in minutes when the system first reached equilibrium. So I would say somewhere around 3 minutes, maybe between 3 minutes and 3.5 minutes. That's whenever the graph looks like it is holding steady, when it first reached equilibrium. Most people got this. There were a few that said 2 minutes. I don't think it was quite ready at 2 minutes. Okay, so things are still decreasing and increasing at 2 minutes. This person says 6 minutes. I think 6 minutes is a little bit too long. Again, that would be maybe after equilibrium was reestablished, after a change was made, but initially reaching equilibrium around 3 minutes or so. And then the person says around 6 seconds. So again, so pay attention to the numbers and the units on the axis. All right, what happened at 5 minutes? Well, at 5 minutes, we have an increase in the concentration of SO2. So most likely more SO2 was added to the reaction vessel. Okay, these people said at T equals 5, the SO2 was added to the system. Looks good. SO2 was added to the container. Then we had some people that were a little bit confused. They said pressure was increased. That's not specific enough. Adding more SO2 is really what we're going for here. A possible change is that the volume was decreased. We don't know anything about that. SO2 definitely increased. If the volume had decreased, then all of the pressures would have gone up, not just the SO2. The temperature was changed. I'm not sure how we would know that. This person says that the change favored the reverse reaction. There is not enough information to denote what exactly the change was. This person says the change that was made at 5 minutes caused the equilibrium to shift toward the reactant side. Again, talk about what happened. There was a spike in the concentration or the pressure of SO2. So after the change was made at 5 minutes, the partial pressure of SO3 increased while the partial pressure of O2 decreased. Explain this observation. So once we add more SO2, we're going to shift the equilibrium toward the left. That's going to cause the SO3, which is a reactant, to go up. And it's going to cause some of the SO2 and some of the O2 to decrease because those are products. Okay, so the increase in the partial pressure of the SO2 was a change or a stress to the equilibrium system. SO2 is one of the products of the reaction. When the concentration of the products increases, the equilibrium position shifts toward the left. Okay, so we added more SO2 and there was a shift toward the left, toward the reactants. You also could have talked about Q versus K. Before the SO2 was added, Q equals K because we're already at equilibrium. And then after the SO2 was added, the Q became greater than K, and this caused the equilibrium position to shift toward the left. All right. Because the partial pressure of SO2 suddenly increased, it is a stress applied to the system. The system would shift to the SO3 to get rid of the extra SO2. That sounds good. Increase in partial pressure of the reactants, decrease in the partial pressure of the products. Since the equilibrium was shifted toward the left, O2 was used in order to produce more SO3. Looks good. According to Le Chatelier's principle, the addition of products will cause a shift in favor of the reactants. SO2 and O2 are consumed and more SO3. Looks great. All right, write the expression for the equilibrium constant expression. Remember that we're talking about pressure here, not concentration. So if you show me brackets, that is incorrect. We're looking for Kp, not Kc. And we have to see P for pressure. Okay, you can't just put the chemical inside parentheses. We have to see P for pressure. All right, that's what I'm looking for. Products over reactants. So the pressure of the SO2 squared times the pressure of the O2 divided by the pressure of the SO3 squared. Could you have typed this? Absolutely. This person writes the letters K sub P, that's fine. They write PSO2, no subscripts. They have a little caret symbol. We know that means a superscript. This is great. Okay, so don't feel like you have to get fancy with all your superscripts or fancy formulas. You can totally type this on one line and we know what you mean. They also calculated the value of the Kp, and I'm looking for around 0.06, 0.07. Looks good. Okay, so just to show you that you could have typed this. You did not have to handwrite this. All these symbols look good to me. Now, let's talk about some problems. Okay, I'm okay with this. This is fine. A little bit strange to have the subscript inside the parentheses, but this is not a deal breaker for me. Looks good. Brackets. Nope, that means concentration. The pressure symbols are there, but it is upside down. It should be SO2 and O2 on the top. They got that upside down. Sorry, no pressure symbols, just chemicals inside parentheses. That's not good enough. Here, that's a plus sign as opposed to multiplying, and there's no superscripts. Here we have superscripts on everything, including the O2, which there's not supposed to be. Here we don't have the superscripts for the exponents, and here we have, again, brackets. So please watch out for your answers for things like this. All right. I'm going to estimate that after the first equilibrium, we have 0.5 atmospheres for SO3. Reading the graph, it's somewhere between 0.3 and 0.35. So I said about 0.33. And again, you could be off by a little bit there. 0.32, 0.34, it's close enough. And then here it's somewhere between 0.15 and 0.2. So I'm going to estimate around 0.17. All right, let's go ahead and plug in those numbers into our KP expression. Around 0.07. Let's go back to the graph. When equilibrium was reestablished, you could have said, well, now the pressure is somewhere between 0.5 and 0.6. So around 0.55 and 0.6, so around 0.57. This looks like it's just above 0.4, so around 0.41. And this pressure is just below 0.15. So again, I estimated this from the graph. Plug those numbers in. So approximately 0.07. I think depending on what the scoring guidelines were for this question, I would say in the range of around 0.06 to 0.08. Again, typed looks good. Handwritten looks good. These all look fine to me. Okay, watch out. That's what it should be. They just read the graph wrong. It's definitely higher than 0.55, so they went in the wrong direction. And then again, it's not 0.72, it's 0.072. So watch out for careless math errors. Okay, again, things like this, don't be careless. 0.17, not 0.27. Now this looks good, but I think they forgot to actually square their number, so they got the wrong answer. And this person set it up, but they didn't actually calculate it. So they plugged in the numbers, but didn't finish the problem. Okay, so again, these are helpful guidelines. All right, is the decomposition of SO3? Endothermic or exothermic? Justify your answer in terms of Le Chatelier's principle and the information in the table above. So when the temperature is increased, it looks like the value of Kp has also increased. An increase in temperature has increased the value of Kp, which means we are shifting toward the products. Okay. And we are raising the temperature. So this is the equivalent of adding heat. We're talking about an endothermic process. Here's what I said. The decomposition of SO3 is an endothermic process. According to the data in the table, as temperature increases, the value of the equilibrium constant also increases. Increasing the temperature of a system should shift the equilibrium position in the direction of the endothermic process. For this reaction, an increase in temperature causes a shift toward the products, so it must be endothermic. All right, reaction is endothermic. Temperature is increased, Kp is increased. Since Kp increases as temperature increases, it must be endothermic. Okay, decomposition is an endothermic process because as more heat is added, it shifts toward the product side, larger Kp value. Those all look good. Now, here's some problems. The decomposition of SO3 is endothermic. Okay, looks good so far. Because when heat was added, the system shifted toward the right. Notice that they never mentioned anything about the data in the table. Okay, the question asked you to justify your answer in terms of the data in the table. They're talking about a shift toward the products, but they're not mentioning anything about KP. Okay, so when you're writing this, good explanation. Before you finish and you move on to the next part of the question, go back and read the stem of the question and make sure that you are fully answering what the question was being asked. All right, little concerns on this one. All right, it's endothermic. This is because energy is being put into the system to break and decompose the bonds. As temperature increases, so does the Kp value. Okay, so far so good. In terms of Le Chatelier's principle, the reaction is shifting to the left. Okay, it's actually shifting toward the right, so that's a concern. It talks about there are fewer moles of reactant than there are product. Le Chatelier's principle says the side with the least amount of moles, now they're really getting confused. So I think they probably had it, but they just kept talking and they said stuff that now actually cancels out some of the earlier good work. All right, I like this. Temperature goes up, Kp goes up. I actually don't know if this would get credit or not, but I want to caution you about this. The question says, is it endothermic or exothermic? The word endothermic never actually appears in this student's response. Now they're showing heat on the left, so I know what they mean, but I don't know if this is enough to show you've actually answered the question. So again, pay attention to what the question was that was being asked. All right, now, do not be discouraged by this particular virtual lesson. I hope that you are not discouraged. I hope you are encouraged to take the time to be more careful, to be more thorough, to pay attention, and to show your best work on the AP exam. Okay, so in my final minutes of this lesson, I'd like to do the following. I'm going to go ahead and show you some answers to questions that were asked in the email that people were submitting their sample responses to me yesterday. These were some questions that were asked. Let's go ahead and take a look at some answers to these questions. All right, a student says, will we be able to use our phones to scan a PDF and then submit it from our laptop? Another student asks, I plan on submitting a picture of my written work for the exam. If I take the exam on my computer, can I take the picture on my phone, then upload that picture to my computer to submit it? Yes, but pay attention to the format. If you're going to use handwritten work and take a photo, the file format should be .png, .jpg, .jpeg, not PDF. If you're going to use a PDF, it has to be text only. So .doc, .docx, .pdf, .txt, .odt. And again, I showed you plenty of examples today where students just typed and they did fine showing their work. All right, the student asks, let's say I'm opting to type my answers on a Word document and there is a question that requires us to draw, for example, a molecular structure. Well, the good news is on the 2020 AP Chemistry exam, you do not have to draw a structure or label a diagram or draw particles. So no worries about that. How should we show proper work on the AP exam if we are typing our responses? Like this, okay? So you want to take a look at how students are doing it successfully. You can go ahead and type, and there is a keyboarding tip sheet that is available that is also linked in the links in the video description. Okay, so you're welcome to type it. Just show your work, show your setup, but you don't have to get fancy with all your superscripts and subscripts. We will be fine as readers to interpret your answer. This question says, this took me much longer than the allotted time. Does this represent how long the questions will be on the exam? I was wondering if we were supposed to be able to finish all parts. Will we still be able to earn a 3, 4, or 5 if we don't finish all parts? Also, if you make minor errors like capital letters for variables, will you be docked points? Okay, here's my answer to that question. You can receive partial credit for a partial answer. However, if you allow the time to run out on you, then you won't earn any points for that response. So it is better to submit a partially completed answer and get partial credit than to scurry to finish and possibly waste time and not have enough time to submit. So it's okay if you didn't answer every single part on the exam. You can still earn a good score. Minor errors in spelling or capitalization will be ignored as long as the reader can understand the basic information about the work that is shown in justifying the calculation. This person said, it would be acceptable for me to handwrite my response, take a picture of my work on my phone, email it to myself, then download, attach it to the AP exam. Yes, you can send a photo or a document to yourself via email. Make sure you use actual size because sometimes the photo is going to get shrunk and then maybe make it difficult to read. Try to keep the process simple. If you can connect your phone directly to your computer, or you can AirDrop it, or use a Google Drive app on an iPhone. If your internet is slow, you might run out of time if you're trying to wait for yourself to get an email. So try to keep things simple on exam day. All right, this person said, if we get the sig figs wrong, will we still get the points? Well, that depends. On a normal chemistry exam, there are 46 points available for the entire free response question, which includes 7 FRQs, and only one of those 46 points is devoted to a particular part of the FRQ for sig figs. Now, if, and I don't know this for a fact, but if there are sig fig points assessed on the 2020 AP exam, again, the sig figs would have to be correct for that particular point to be earned. So I would just say pay attention to sig figs because you never know if they're going to be included. Respect the sig figs as you're solving problems, but do not worry, it would only be 1 point out of all of the points possible. In the actual test, will we have to do written calculations as well, or will it be solely typing? It's both. You should expect a variety of question types. Some questions require a numerical answer with calculations shown, and some questions will require an explanation in words. My handwriting is really messy. Should I be concerned on how it is graded? Well, if you're notorious for messy handwriting, then you may want to choose to type your responses so the work will be easier to read. All right, well, thank you all for hanging in there. I'm sorry this virtual lesson ran so long. This is my final slide. It shows you important links to a variety of websites that will help you prepare for the AP exam in 2020. In tomorrow's lesson, I will present timed questions for you, just like we did on Monday. All right, thanks everybody for watching. We'll see you tomorrow.